Okay, our next speaker will be McClure from New York Road, and she will tell us about perfect numbers in quadratic fields. So I'll turn over to her.
Hi, I'm McClure. I'm from here, Molloy, and my topic is perfect numbers in quadratic fields. So a perfect number in our regular integers is just a positive integer n such that sigma of n, where sigma is just our sum of divisors function, is equal to 2n. So our first perfect number is 6. So you could see that a sigma of 6 is just equal to 12, which is clearly 2 times 6. And then the next one's 28, sigma 28, 2 times 28. And a nice property to have is that sigma is multiplicative, which just means sigma of a times b is equal to sigma of a times sigma of b when GCD of a and b is 1. So because we have that nice property of being multiplicative, we can use prime factorizations in our sigma function. So this is just what it comes out to be if n is equal to all these primes. This is our prime factorization. And then we have an example down here of 28. And we just use its normal prime factorization and still comes out to be 2 times 28. So my goal is to define them in quadratic fields, but to do that, we need to know what integers are in quadratic fields. From that, we need to know what prime is. We need to hope for unique prime factorization. And then with that, we can have a sum of divisors function. And then to define perfect, we need a sense of even, obviously, because it's 2 times the number. So this is a quadratic field for a square-free integer d not equal to 1. Q of square root of d is equal to x plus y times square root of d, where x and y are rationals. And this is a quadratic field. So obviously what I want are integers. The ring Z of square root d, where a and b are just integers, it is a subring, but these are not, they act like our regular integers, but sometimes this is not our only integers that we have in quadratic fields, so we need to be careful. Two important functions that we're going to use are the norm and the trace. So if alpha is an element in our quadratic field, the norm of alpha is just alpha multiplied by its conjugate, and that comes out to be a squared minus db squared. And then the trace of alpha is just alpha added to its conjugate. So that just comes out to be 2 times a. And then I have an example here of where 5 plus square root negative 6, and that's in the quadratic field q of square root negative 6. Its norm comes out to be 31 and its trace comes out to be 10. Our norm is multiplicative, our trace is additive. And this is where the elements of a quadratic field are coming from. Every alpha in a quadratic field is the root of a monic polynomial of degree 2 with rational coefficients. So what that just means is x minus alpha times x minus alpha conjugate. And that comes out to be x squared plus trace of alpha x plus norm of alpha. So from this, we can get what the integers are in a quadratic field. So what the integers are is just when trace and norm are integers. And that comes out to be z of square root d. These are integers since norm and trace are integers, but these are not the only integers. So if d were to be congruent to 1 mod 4, and we had this example alpha equal to 1 over 2 plus square root d over 2, then alpha clearly isn't in z of square root d, but the trace does come out to be an integer and the norm comes out to be an integer. So this makes this an integer in a quadratic field. So these are our integers in quadratic fields. We have if d is not congruent to 1 mod 4, we just have z square root d. And then when it is congruent to 1 mod 4, we have a plus b times 1 plus square root d over 2. So when it's not congruent, it's simple. It's just z of square root d. And when it is congruent, it's bigger. So just like, I'm just going to be referring to it as z of omega. So it's simple, but omega is just the 2 different cases. So one important property that we get from the norm is that if the norm of alpha is equal to 1, alpha is a unit. So in z of square root negative 14, the units are just plus minus 1, because the only time that we get 1 when we're taking the norm of an element in here is when a is equal to plus or minus 1. But if we look at z square root of negative I, the norm just becomes sum of two squares. So this is equal to 1 when a is equal to 1 and b is 0, or if a is 1, a is 0 and b is 1. So that makes the units plus minus 1 and plus minus I, since it's just square root of negative I. So a non-zero alpha in z of omega is irreducible if alpha is not a unit, and in every factorization alpha equal beta times gamma, either beta or gamma is a unit in our integers. So this sounds like prime, but it's not the same. We just have irreducible right now. So, but if norm of alpha is prime, then alpha is irreducible. I have an example here of another element in z of square root negative 14. 3 plus square root negative 14, the norm of that comes out to be 23. That makes that irreducible. So when is prime and irreducible the same? If an irreducible element alpha has the property alpha divides beta gamma implies alpha divides beta, or alpha divides gamma, then alpha is prime. So that's just Euclid's lemma in the integers. And when this is the same, then we have irreducible and prime are the same. But this does not always work in every set of integers of quadratic fields, like in z square root negative 5. We have two different factorizations of 9, and these are both factorizations of irreducibles. So we have 2 plus square root negative 5 times 2 minus square root negative 5, and that equals 3 times 3. But 2 plus square root negative 5 doesn't divide 3 times 3. So that just means it's irreducible, but it's not prime because it doesn't have that property. And then this is another interesting example, how we have two different factorizations of irreducibles of 81, but on one side we have two different factors, the other side we have 4, but these are still both factorizations of irreducibles. But it is true that every single non-unit in the integers, it is a product of irreducibles, but we don't always clearly have unique factorization into it. But for some special cases like q of I or square root negative 1, we do have unique factorization. So this is a special case. The integers of q of I are known as the Gaussian integers. Many of their properties are shared with our ordinary integers. We have irreducible and prime to be the same thing. So we can prove unique factorization with this. The units, as I said earlier, are plus minus 1 and plus minus I. So associates of alpha are plus minus alpha and plus minus alpha I. So we're going to need to consider this in our prime factorizations of elements. So prime Gaussian integers are basically if we have a Gaussian integer alpha, and alpha only has the factors plus minus 1, plus minus I, plus minus alpha, and plus minus alpha I, then alpha is prime. So it's like in our regular integers, if we just had n and plus minus 1 and plus minus n are its only factors, then it's prime. It works the same here, just we have more different factors because we have more units. And same thing goes, if the norm of it is prime in the integers, then alpha is prime. So here are two examples here. And this is just the definition of unique prime factorization in the Gaussian integers. So if we take alpha to be a non-zero and non-unit Gaussian integer, and we have two different factorizations of it, in our ordinary integers, we could probably match it up 1-to-1, but here we have, they're unique up to, I'm not unique, they are the same up to reordering, and that for every pi I, it's equal to u times pi I prime, where u is a unit. So u could be 1, negative I, and that'll make them look very different, but you will see you can just pull it out and it's the same exact thing. And we need to allow this in our unique prime factorizations. So here we have two different factorizations of 5, and all these factors are prime, and clearly the primes like in one don't appear in the other. And this does not violate uniqueness or anything, because allowing the unit multiples, we can pull out a negative I of the 2 plus I and get a 1 minus 2I. And then on the other one, we could pull out an I of 2 minus I and get 1 plus 2I. So it's literally the same exact thing that we have in the regular integers. If we had 10 being equal to 2 times 5 and then -2 times -5, we'd have to pull out a unit, and that's the same exact thing. But we avoid this because we just use positives in our prime factorizations. Clearly, we can't do that in the Gaussian integers. But this is how we find prime factorization. So if we just use our norm, because the norm is multiplicative, so it works out nicely. So if we had like alpha to be equal to beta gamma, that just means norm of alpha equal to norm of beta times norm of gamma. So here's an example. If we use 3 plus 7i, we take the norm of it, we get 58. So we use the prime factorization of 58 in our regular integers, which is just 2 times 29. And then we ask ourselves, can we write that as a sum of two squares, which we can? So that comes out to just be 3 plus 7i comes out to be 1 plus I times 5 plus 2i, because we just find the numbers that work, and then that's our prime factorization, and these are both primes. So now we want to create a sum of divisors function in the Gaussian integers, but what we want is the same type of properties that we have in our regular integers for it to work nicely. So if we have sigma of pi to the n where pi is prime, we want it to be equal to the same way we have in the integers, 1 plus pi prime, all the way up to pi prime to the n. But obviously pi prime is an associate of pi because we want it to work nicely, and we have all these different units that we pull out. While in our regular integers, we don't do that. We have just positives and it's simple, but here we don't have really a sense of positivity. So we need to choose the correct associate to get these two properties. And to do this, we just choose an associate that's lying in the first quadrant, which just means that a and b are both positive integers. So if we take a Gaussian integer and then we make this our prime factorization, and notice that I have a u pulled out in the prime factorization, that is a unit. So it could be 1, negative I, or I, and then all these pi i's are primes. Then it comes out literally to be exactly the same as our regular integers. But remember that we're pulling out the unit. So for example, we have 2 to be equal to 1 plus I times 1 minus I in the Gaussian integers. But if we pull out a negative I from 1 minus I, then we get negative I times 1 plus I, just so 1 plus I squared, where negative I is that unit that we're pulling out. So then we could just use the second prime factorization, and then it works the same exact way as our regular integers, and that comes out to be 2 plus 3i. So now we could define what a perfect Gaussian integer is. So when the norm of a Gaussian integer is even, then the Gaussian integer itself is even. But also we have this nice statement where a Gaussian integer is even if it's a multiple, if and only if it's a multiple of 1 plus I. And clearly you could see that the norm of 1 plus I is 2. So it kind of matches up to our regular integers. We have that sense of even. So one example of even Gaussian integer is 5 plus 9i. The norm of that is 106. That's clearly even. That makes that even. We must be able to write it as a multiple of 1 plus I, which we can. And then when a and b are both even, or if a and b are both odd, then that's going to be even just because it's a squared plus b squared. And then to match up with the definition of perfect in the integers, a Gaussian integer is perfect if sigma of alpha is equal to 1 plus I times alpha. So it's like the same thing, 2 times n. And then the obstruction in like just any like form of integers of quadratic fields are just non-principal ideals, because the elements are like in our ideals kind of reflect the ideal itself. So if we have a principal ideal, then we can have unique factorization. If we don't, then we have those weird factorizations where it's not unique. A few examples for D are just 13, 5, 2, -2, -3, -7, -11, etc. But I think there's like exactly like 9 negative values and then a couple of positives. So if you wanted to like define perfect in those, you would need to have all these properties, like what's going to be an even, what's going to be a prime, and that might come out to be different because the norm comes out to be different every single one. But yeah, that's it.
Do I have any questions for a speaker?
What made you interested in this? Just like the perfect number problem itself, like because we don't know how many there really are, or if there's an infinite amount of them. So I think it should be interesting to see if I push it over to another.
Bigger speaker again. We'll start our next presentation at 9:35.